nonetheless, our last speaker of the day for the workshop comes to us from the University of California, Santa Cruz, and is the director of the UCSC Systems Research Lab there and the director of the UCSC Los Alamos Institute for Scalable Scientific Data Management. I guess when you buy a house, it's location, location, location. When you're dealing with big data, it's management, management, management. Anyway, he's also an associate adjunct professor of computer science there, and he's been there since 2005, I believe. And his interests range from scalable file system data, metadata management, storage, metadata, QoS, a range of issues, and I don't want to read them all. And so, without any further ado, yes, exactly. Carlos Maltzahn, please.
Thank you all. Thank you, Stephen, for the introduction. Thank you for organizing this. I really want to thank the organizers. This is a great thing. I've never been to a workshop like this that's so hands-on, and I just love it. I mean, unfortunately, I couldn't really participate in every of these sessions because I get called into other conferences. But I like to stress that I'm here to learn from you, and we have, and to also announce a new effort that the NSF has greenlighted. We haven't gotten the money yet, which is called the Big Weather Web. And I'm going to spend some time at the beginning to introduce you to this project. Some of us are on this project, and then the other part of this hour is mostly led by my student Eva Jimenez over there in the corner. And it's going to be a quick introduction to Docker and also some experiences that we think are key experiences that we want to enable with Big Weather Web and Docker. You know, we're basically and other virtualization technologies. So let me just introduce myself a little bit more detailed than Stephen just did it. There are a number of long names in there. I seem to attract director positions. I don't know why. It seems like somehow they congeal on me. It's probably because I'm an adjunct professor and not actually a real professor. And an adjunct professor doesn't actually have a teaching load. I teach like maybe 1 or 2 classes a year, but have more time to do other things, including research and advising students. One unusual thing about adjunct professors is that they usually do something else. But I'm an adjunct professor 100% of my time, and I'm raise my own funding, raise the funding for my students, and have been done so for the last 10 years. Before that, I worked as a performance engineer at NetApp. I have a very, a pretty industry-related performance engineering background for storage systems and network intermediaries, like web caches. Okay, so my current research is very large-scale storage systems, and the way I got involved into this community is kind of through unusual means. So Josh Hacker, who used to work at the Navy postgraduate school, I think it's called, in Monterey. He heard about my work and one day cold called me, and we met, and shortly thereafter organized an NSF-funded workshop about the barriers for this community to big data. And we proposed Big Weather Web, and this is sort of the outcome of that conversation. And so it's, I'm really thrilled to be able to contribute to weather and climate research and to provide, make my research useful. So I want to also introduce my student, Eva Jimenez. He is a PhD student for computer science in UC Santa Cruz. He's also a doctoral fellow from UC Maxus in CONACYT. CONACYT, I don't know whether you know, is the NSF equivalent in Mexico. And he's a member of my research lab, it's a systems research lab, and is also a software engineer at Red Hat. And he has also work experience at Intel, HP, Teradata, and Lawrence Livermore National Labs. His background, which is kind of unusual, is both data management and storage systems. So he has a very strong database background, but he's also really well-versed in storage systems. His PhD topic has nothing to do with either of them. No, but it's basically reproducibility of systems and systems evaluations. And actually, a lot of the versioning and transactional background he has comes into play there. So for now, I just give you sort of a quick overview. I said already at the beginning, I'm first going to introduce the big weather web. Then Ivo is going to give a quick introduction to Docker. And then we are going to provide two experiences that is sort of more a hands-on exercise. The requisites, or the requirements for doing these hands-on experiences are on this website. So let me start with the big weather web. So it's a common and sustainable big data infrastructure in support of weather prediction and research and education in universities. So that's actually an outcome from a lot of EarthCube workshops, as some of you probably have attended, where EarthCube Users Workshops, where people were sort of trying to get a grip of what is it that's missing that will, give you better access to big data technologies. The project, I say NSF funded, but it's actually only NSF green lighted. They said we have the budgets submitted. We just have to clarify a few little details, but I think it's pretty much clear it will be funded. It's a software integration project, a scientific software integration project as part of the Infrastructure for Sustained Innovation program at NSF. And the goal of these projects in general is to create a sustainable community software framework. So this is not a research project. This is a project to actually put together a framework that has certain properties that we believe are essential for getting this community, giving it access to big data. They're the collaborators. So I'm leading this effort at UC Santa Cruz. Then we have subcontracting relationship to Jeff McWhirter at Geosystem. Don Murray at NOAA is also doing consulting. Eva Jimenez is the student at UC Santa Cruz who's working on this. We have Unidata as one collaborator. Kevin Tile is associated with the University of Albany, but he's also very much involved in Unidata, and so he's our part of the lead collaboration team. And then Gretchen Mollendor, who is, I hope I didn't, Mollendor? Yeah. Who is also sort of our interface to the other collaborators, which is the 7 university ensemble prediction team. And so these are the domain experts, right? These are the people who are sort of the clients of what we're trying to build and are directly involved on multiple levels to make sure that we build the right things. They're sort of validating our research and then also improving it. We want to very much create something that is fully can be adopted by the community and is something that's not just thrown out there and use it or lose it or something. So the problem that we're trying to address, a little more detail about that. We recognize the problem as a threefold component. It has 3 components, right? One is, and we think that is actually the key problem, is poor reproducibility of data-intensive science. And that's very well known. This is something that happens everywhere in all scientific disciplines right now, including computer science, which some argue is that really a scientific discipline. But and it has a huge impact on not only on research but also on education. And The other part of the problem is, and that's related to reproducibility, it impairs your availability of intermediate results. You can't really build on other stuff if you can't reproduce things. So you do a lot of extra work, and there are steep learning curves. And so the result is really that communities fall behind. And they can't really adopt a lot of the new technologies because they have still practices that kind of cement them in the past. I like that wording from Brian earlier today. You get cemented in the past too much. You can't move forward anymore. So the domain is numerical weather prediction. Right now, a lot of these universities have some access to supercomputing through grants. Then they produce a bunch of data, and then where is that data going to be stored? Right? They have some local resources, but then they need a lot of maintenance, and it's not clear whether they can trust those resources themselves, but maybe somebody else won't trust those resources, right? Or they can keep them in scratch space, but everybody knows that scratch space, after 2 weeks, you get thrown out. So you can't really share your results very well. You don't have really the infrastructure at all to do that, and the trust that's necessary for that. And then, you have a culture where you're rewarded for results, not data. At the university, you don't get tenure for providing a bunch of data. You get tenure for publications and funding. So the general approach that we selected is this concept of nuclei. And these are pieces of technology that are easily shareable and that have an ability to grow and be improved, and they ensure sort of buy-in by the community. And there's really two big examples for what we think are these nuclei, right? Is Wikipedia. It's something that everybody can work on, easily get involved in, and can improve. And Linux kernel is another great example, right? Where an ever larger community can contribute and great things happen. They happen very incrementally, but because of a certain infrastructure that the Linux kernel community maintains, that incremental improvement is really working out, right? So for the big weather web, we identified 3 nuclei. And the first one is a large ensemble distributed over 7 universities. So this is, in some sense, our test case. It is basically a data set of predictions with different ensemble members. And don't ask me any details because I do not understand the full details here. But these people and at these universities are involved in creating this ensemble. And the key is that no one can really store the entire ensemble locally and doesn't want to, but that actually collaboratively you create a situation where everybody has benefits from different ensemble members that are contributed from different universities, right? And in order to do that, the second nuclei, and I should say the first nuclei is, the thing that is improved over time is essentially these ensemble members and the refinements of that for education as well as for research. Right? How would you manage that? What are the things that are valuable? How you refine the data set and so forth. At the second nuclei is a common storage, linking, and cataloging methodology. That methodology is, the implementation of that, we call the data investigation and sharing environment. And I will talk a little bit more about that. There's a colon, but ignore that colon, that comes later. And then the third nuclei is a virtual machine container technology for easy deployment and reproducibility. And it's these 3 things that anchors us in a particular domain that allow us to share and to incrementally build upon different contributions, and to make sure that we can do so even in the presence of rapid change as we have in our computational environments. So let's talk a little bit about the first nucleus. Are there any questions so far? I want to keep this interactive. Yeah, go ahead, please.
So the second one with common sharing, like, kind of sounds like a common file format that we've gone through before. I would think it's more important just to document the storage format and to actually have the exact same format. Could you comment on the importance of actually having exactly the same storage format?
You jump to conclusions here because we don't talk about storage formats. It's a methodology. It has nothing to do with formats. I mean, there are many, many formats we're going to come.
Not the file formats, but the
okay.
formats of how you store the data.
Yeah, same thing.
So
no assumptions there.
So what's the common storage that you're talking
Think of it more like a way that we extend the World Wide Web. And we manage the web servers that meant, that so you can have certain you have certain assurances about how these web servers operate. I will get into that more detail. So in the first nucleus, let's see. So it's basically, the first nucleus is really about the testing this distributed ensemble framework and tools, and then sharing this knowledge, the products that come out of these distributed ensemble, out of these ensembles. And some of these are initialization methods, physics options, and workflow scripts for producing and analyzing data. One really important thing is if you share data, and if you want to actually get your community to acknowledge the value of sharing data, is to track actually data authorship, right? And there is currently no good infrastructure out there that actually does that, right? If you share something on a web server, the web server doesn't keep track of how many times you access something. I mean, you can go through the logs, but that's kind of you have to look at unique users and all that stuff. So it's a lot of effort to actually figure this out. So this is something that's really important for this infrastructure and the framework, that we track authorship and how it actually not only track authorship, but how that data that you published impacted the community. How much is it referenced, just like publications, right? And then, of course, the dissemination of framework and tools that make all this possible, right? And so that this is basically then ensured by the other nuclei. So there are 3 levels of participation in this nucleus one. We have these 3 levels, and so these 7 universities, the way they participate is basically first, and that's the most basic level, and everybody participates in that level, is to contribute ensemble members and with tool testing. And that's once every 3-day forecast of a 12-kilometer Carnos domain for 1 year. And then 1+ ensemble member per university. So every university at least provides 1 ensemble member. And then the other two levels, level 2 and level 3, are sort of parallel. One is level 1 plus an educational integration of the findings of this activity, and the other one is a research integration of the findings of this activity. How can you integrate the ensemble members in your research? So these are the people that are involved and the participation level. Pretty much everyone is involved on level 3, which is the research integration, but Gretchen is level 2, and Steve Graybush at Penn State is only involved in level 1. So I can sort of go through the different particular different focus of the different universities, but I don't want to spend too much time on it, and you can look at those slides later on. But I want to move on to Nucleus 2. So Nucleus 2, Nucleus 2 and Nucleus 3 are basically the technical core of the software framework. And it's the most likely one that we can hopefully also transfer to other communities if they are successful. So we'll see. So think of it as the following scenario. And I think we'll also hear on Thursday somebody who's going to talk about publishing and reusing these publications. You have figures in your PDF file. And PDF file already supports links. You can click on this figure and you get transported to a website that gives you information about how this figure was generated, what tools were used, and what data was used, what data product. But you can not only do you get that information, it's not just written there, but those are links as well. And you can also, you can download the tool, you can download the script and how the tool was configured. You can reproduce that figure. You have everything you need to reproduce that figure, including the data. But then you can actually change the script of the tool. You can add more data that you produced. You can then directly compare it with the other data in your own visualization, right? So this is the kind of level that we want to create. And there are some examples of that already. But there's, I think the key thing here is there are a lot of technologies out there that can help you with doing that. But again, this is a project where we integrate these technologies and make that available, right? And think of it, what that actually means for your classroom. When you teach a class, and you not only give students a paper to read, but they can actually, with every figure that's in that paper, can actually play with the data, play with the figure, play with different ways of looking at the data, right? A completely different experience. And so, and it's really important to create an environment where that form, whatever link, whatever provenance, there are many names for this, how that is actually provided. And we really want to get to the point where it is reusable, right? You can actually take that figure and you can change it, you can update it. The person who created that figure will get credit for having that figure, done that figure, and there is a provenance trail from your figure that's building on top of that figure, right? When you publish a paper and you compare it to earlier research results, right? All those tools and data and so forth that have been included in the original figure will also be continued to be referenced. So this is and all this stuff is possible today. It's just not put together in such a way that it's practical. So this data investigation and sharing environment is, you can think of it as a federation of geographically distributed nodes. Each of those nodes are appliances. With an appliance, I mean something that just works, right? You don't have to configure it. There's no complex stuff going on before you can run it. It just works like a toaster. You go in the store and it's a toaster or an oven or a refrigerator, right? It's very easy to use. And the reason for that is we found, and that's one of the key insights for me at least in this workshop that we did in preparation for this proposal last year in January, was that there's the fundamental impediment for people to share data was actually, so there was one thing was actually able to share the data, but the other part was, would you then download the data, or would you just rely on the other party to have that data available? And that's the key thing. There is no trust today that that data is available, right? That other university will have that data available there, that they have the resources to have that data available, right? So you can say, well, let's put this data to the cloud, but then, the cloud services are always available, but only as long as you have the funding to pay for them, right? So the cloud services don't have that model, or are not compatible with the funding model that you have, where you get a bunch of money for 3 years and then the funding runs out, and what then, right? And so that's why we also have different deployment types. So you can put these appliances on the cloud when you have money to do that. Then you don't have to worry about all the maintenance. But you can also run it in a private cloud, or you can run it on actual hardware that is community recommended, right? We will have hardware specifications that the community, like Unidata, for instance, can provide as part of the Unidata Hardware Award. And is that the right name? Kevin, you correct me if I'm wrong. This hardware will be then pre-configured, pre-tested for this particular application. All these things are subject to community-driven review. If something doesn't work as planned, or some other parts, unforeseen shortcomings, there's feedback. There are people responsible for improving that, and then there will be new releases of those appliances. So this is sort of the overview. These appliances can run on universities. They can be in the cloud. They can, there will be almost certainly one appliance will run at Unidata and at INCAR. Maybe more. So what's running on each of those DC nodes? For now, we think it is probably a Ramada instance because it's a very extensible cataloging service. We will extend the Ramada with big weather web plugins that knows how to link to remote resources, other DC nodes, as well as accounting for resource usage, right? As I earlier said, that's going to be really important. Then there's the other part of that, what's running on the DC node or DICE node, I don't know exactly how to pronounce this, is appliance software, right? That's stuff that makes it really easy to use. And particularly, it keeps track of whether your data is safe, which is the most important thing. And since these nodes are federated, it can actually keep track of copies that are stored on multiple nodes. And it will make sure that some of the data that is particularly valuable will be stored on multiple nodes. And it will check whether that node is still up. And then when that node is not up, or somebody decides to delete that copy, it will basically alert you to say, you better find another place to get that copy. Some of that will be automated if you have enough DC nodes, so you can, there's sort of space management. Some of the space that you provide on the DC node will be reserved for making these assurances. And so it basically, as an appliance, it will make sure that best practices for keeping data safe are followed. You don't have to worry about that. The software will either give you instructions or automatically do the right things to keep the data safe. And then it uses best of breed local storage software. It might be ZFS, it might be not ButterFS, that's a little prototype. But a lot of open source, there are a number of open source alternatives for very robust local storage systems. Then any questions for Nucleus 2? Yeah.
So who's ultimately responsible for making sure that the data is preserved forever?
Ultimately, it's the data that you contributed, that's your responsibility, right? The PI is whoever produced the data. But as a technological who is responsible for the technology? It's going to be, whoever adopts serving that. Right now, for this project, it's going to be Unidata. And Jeff McWhirter at Geosystems for the Ramada part, right?
Unidata is not going to be responsible for hosting?
The hosting part, again, this is not supposed, it's not only be hosted on Unidata resources, right? It's going to be hosted on various platforms.
Yeah, I mean, it's going to be federated, but I thought that whole idea of getting an DOI is you got to have that available in perpetuity in the future forever.
Yeah.
So the question is, who's responsible for ensuring that? I mean, if your consortium breaks up in 5 or 10 years,
Right.
Who's going to be, because when we publish papers, we put them in libraries, and the libraries are responsible.
So think of it as like this way, organization live and die. And if you make any particular organization responsible, that is almost as insecure as, making a single person responsible on the long run, right? If you look at like 10, 20 years. So the way I'm hoping this is going to work, and this is certainly an experiment, and there's a lot of research, ongoing research about, digital preservation that's ongoing, is that the community will ensure it. And you do this by providing technologies that when you find that like a copy is endangered of some particular data, it will be easy for you to ensure that you can counteract that danger, right? So let's say you have one of those nodes, and you care about a particular part of data, and you think that's endangered data. You can store it, and you can contribute to the effort to preserve it. And I think you can. The technology provides you with ways to directly contribute to whatever threat you're perceiving, to avert that threat. It's not something that you just have to like call somebody and like, hey, why did you keep track of this? It's actually everyone in the community's responsibility to make sure that this is not happening. But we make it very easy. The technology makes that very easy to do.
So I would think that might be a role for a recall or something like that, kind of facilitate that.
Yeah, and that we can, that should be something that we certainly are collaborating with NCAR. But it's a very good question. I mean, I very appreciate that question because it's both a social organization, institutional question as well as a technical question. But the technical question is really the part where we might want to make this as easy as possible, and particularly want to alert the community that something is endangered, right? Some data is endangered. Any more questions?
So
yeah.
Just getting concept straight then. So in that case, if someone perceives a danger and they decide, I want to become involved in this, do they then become a node? And
Yep.
then you basically replicate an appliance on this new node, bring the data.
Yeah, so
I assume that's a partly automated process. I mean, you have to create an instance of the node.
right, you have to create the instance of the node, and then, but then once the node exists, there's going to be a way to say, this is my data, or this is the data that I want to host, right? So presumably you know what data it is, but you could also just say, I want to contribute safety to the system, and then just open the node for whoever wants to use it, right? And then the system decides which are the most important pieces of data, given your capacity to store at your side. Go ahead.
I guess related questions, thinking about this. Is there any duplication of data across these different nodes? Because a lot of like kind of the GitHub model is that you have multiple repositories that kind of have the information and multiple locations that it kind of comes along with you.
Yeah, and both the metadata and the data, is replicated for safety. And we don't talk about, the problem really is not, this is actually sort of earlier mentioned as what was it, the term, not medium data? Was it medium data? Yeah. So it's a medium data problem in some sense, right? The data is not super, super big. It's just big enough to cause you grief. And so replication is very much an is a possibility, right? There's some bigger data sets where replication would be prohibitively expensive, and I don't think we're in that phase yet. Any other? Yeah, please.
So, how do you compare your approach to data one? You're also evaluating.
Yeah. Oh, I'm. No, but I anticipated that question when I saw your talk, and I thought that was very interesting. I haven't made up my mind exactly how that actually compares. I need to know more about Data One. I'm sorry that I didn't look into it more. But there are similar efforts, for sure, to this. I think we have there are some, we differentiate ourselves perhaps with the way we think about these nuclei, and that they are very much, improvable by the community, so that you don't get a web page and information and then you click on it. It is beyond just the web, right? It's basically how we assure that the web servers are there, how we assure that the naming is preserved, that the resources continue to exist. I think it's the other part that the web falls short. And it's also, I think, the other part that we are thinking, and we are sort of gaining new ground, is this appliance idea that everybody can contribute with their local infrastructure as well as cloud infrastructure. Yeah, go ahead, Jeff.
Yeah, it's time to say, at day one, there's a lot of work about sort of replicating data in kind of the back end API.
Mm-hmm.
And what we're really looking at is sort of taking that federated approach, where we have this constellation. There is no one repository. We have a constellation of these appliances running all in our communities or wherever. And but we're going to rely on the services to make that data accessible and visible. It might be some of those appliances are really, really important, and you will clone them, and you'll have direct replication of them. But others, we want to be able to foster this heterogeneity across, even something as limited as weather forecasting. There's a lot of data there in terms of data and content and knowledge and all that stuff. Whereas I think, again, data one is as that back end or just basically doing that replication side.
Yeah. Thank you. Does that sort of answer your question? I mean, we can definitely talk. Yeah, definitely. I would appreciate that. Any more questions? So I'd like to move on to Nucleus 3, which is the virtual machines. And this is sort of the core technology that we're using to enable a lot of this stuff, right? The appliance-like behavior, the deployment. So it's really, as you probably noticed already in this workshop, kind of we used a lot of ways to make it very easy to get set up, right? And it still doesn't work perfectly, but there are tools out there and there's activity out there that works really hard. A lot of people work very hard to make deployment as push button as possible. And that actually changes a few things. It's not just easier, right? So I remember when the World Wide Web came along with Mosaic, the browser, some of you might remember that as well. There was this idea, well, there's nothing technically new here, right? I mean, I could just FTP to this website, I could download this picture, I can take my tool and look at this picture. What's new here? It's a little more convenient, right? I just click on a link. And then it took off, right? Nobody doubts the significance of the World Wide Web. I think that something similar is happening now with deployment of software with tools like Docker. And Eva will go into more detail into that. but it has actually a number of consequences on how you depend on standards, how quickly you can set up fairly complicated systems on the fly, and how quickly you can tear them down, and how much you depend on really a particular environment, right? And I think that it has implications to all kinds of design levels. So we are sort of in the middle of this revolution, and people say, well, there's a lot of hype about this, but I think there is hype, but I think there's also a little bit of an unappreciation of what that actually means. So push-button deployment is a big deal. The thing that we want to use in Nucleus 3 is 3 ways. So we want to, virtual machines, when we say virtual machines, we loosely define it. There's full virtualization, which is the virtualization where you take essentially an entire x86 machine, and that's your virtual machine image. Or you use Docker, which is an example of para-virtualization, where it's above the operating system. So you assume that you always have a Linux operating system, and then everything else on top of that is in your Docker image. So much more lightweight, but of course also more dependent on Linux. But virtual machines are a fantastic vehicle to achieve self-containment. It's a much stronger packaging paradigm than exists, the normal software packaging systems, which were fantastic by themselves, but I think we are sort of on a new level. They can be instantly deployed in common environments. Docker, for instance, you can instantly deploy it in Windows once you have Docker installed. And it provides you with a very neat way of versioning and naming reference points to really complex environments. And that's actually the biggest deal. You can now, just like on the web, you can, with a single click, get something as complicated as a Google spreadsheet or a Google, document. You can do that same thing for establishing a particular environment for executing something or, achieving something. In particularly, it serves reproducibility. We have, so you basically store and run a computational environment. You can archive these virtual machines and reduce the impact of this rapid change that we all experience, right? Our computational environment changes all the time, right? We have security patches, we have this and that, there's new operating systems. My laptop updates itself every night with something, and it breaks certain things sometimes if I'm not careful. With these environment management, I'm much less sensitive to that. I have insulation from all that stuff. There's also active work on actually extending that to distributed environments. Docker, I think there's this sub-project called Swarm that allows you to actually deploy entire Hadoop clusters in the virtual environment. And if you integrate this with versioning and release management and use powerful tools like Git, like the Linux kernel systems, then this is actually a very nice way to achieve reproducibility. And education, we just have to look at this workshop. It's much easier to talk about an experience when you have a shared environment and you don't have to constantly translate that to your own environment with your own idiosyncrasies and all that effort that goes into making an example work. But most importantly, this is actually where community learning takes place, right? So I can improve with each version of this in virtual environments. I can improve how my community works. right? Everybody can contribute to this, and it's sort of this common reference for improvements, right? Anyway, so I want to stop here. I'm already over time. I like to call Ivo. Yeah, you have questions. Sorry.
Question.
Yeah.
What about copyright? Notice it's not on your software, your virtual environment. How are you going to handle all the different copyrights, all the different
Yeah.
packages?
So we will not allow anything in virtual environment or in virtual machines that we can't, right? That doesn't have a compatible license.
Compatible with what? So even if you copy back one, you have many different licenses that are available.
That allows that I can copy,
You know,
that can make as many copies as possible, and that I don't have to keep track of who is, it's like open source software.
yeah, but open source software has several different licenses.
I know,
And
yeah.
are you going to restrict it to one particular license or a group of licenses?
So we want to. So Unidata has a policy to use MIT-style licenses for their products. We can't enforce that, of course, for all products. So we want to ensure that whatever we dedicate, things that we dedicate to the big weather web, which is sort of directly as part of that project, is going to be some permissive license, which is like MIT or VSD license that allow you to take copies and do whatever you want to do with them. But there's other software that maybe has copyleft licenses where I have to keep track of how I combine things and how I contribute to this. And so, sure, that can be also part of the virtual machine, as long as it remains open source. But I think once we get to shareware, this is becoming much more complicated, and we probably say, no, can't do it.
And I heard something with the federal labs that they have weird issues with their copyrights and stuff. That I was told that they can't even copyright a lot of stuff.
Well, they're everything. So we can take that offline because I think we're running out of time. Because I have another effort going on that has to do with open source software, and I can, yeah. But it's really an interesting question, and I appreciate your question. All right, any more questions before we go on to Docker? All right, thank you.
All right, so it's going to be a very brief introduction. Carlos talked about deployment, cloud computing. They suffer this all the time. And people talk about the matrix of hell, which you might be developing one laptop. But then at the time where you have to deploy, that means you have to actually make sure that everybody else will see what you are seeing in your local environment. That's when things start to get crazy. And in the transportation industry, there was a similar problem. You had to ship stuff somewhere else. And there was different ways in which you could transport all these things. So in the 30s, someone came up with the concept of a container. And that had a huge impact on transportation. Like it just exponentially grew from that point on. Because you don't have to worry. I mean, you have separation of concerns. That's the analogy that the Linux containers have in this Docker world. That is, you just worry about building your container, and you don't have to worry on whether or not it's going to run. So you solve this problem, at least in the great majority of cases. So the mantra is build once, run everywhere, run everything. And this is the logo of Docker. So if you were wondering why, this is the whale with a lot of containers on top. So what is a Linux container?
You can think of it as a lightweight VM, like Carlos mentioned. Is operating system level virtualization, where you don't have a hypervisor, so that you have bare metal performance, and it's a sandbox process basically. If you're familiar with change root, if people here have Linux experience, it's basically that, but on steroids. This is diagram. You basically are blowing out the hypervisor layer and the guest OS layer and running on the host OS. And that gives you all the nice performance properties, containers. So again, this is if you were running on the host, you have a bunch of like 170 something processes running here. If you get into a container, then you just see your process. That's the only thing that runs in that machine. So if you were able to install this Docker, how many people were able to install Docker? I see. Well, I mean, maybe we have some time after this, right, to just hang out? Okay, so maybe we can look at it in a minute. Yeah, yeah, Windows is a little bit hard to, I mean, depending on, but yeah, it's, we'll look at it. But the idea is you have a registry that it's in the cloud. The default, you can have multiple registries, but the default will point to Docker, the company. And they have a huge repository of machines. And, well, this is installation. So the most useful command is the help command. You do Docker help, it will give you a brief description of all the things that you can do. And then if you want to know, if you want to get further help for a particular command, you do Docker help and then the name of the command. And that will give you particular help for that command. There's an image that it's called the hello world image. It's very small, so if you do Docker pull hello world, it will take like a couple, less than a minute to download. And then if you do run hello world, it will actually launch a Linux machine. Okay. Yeah, I'm basically almost done. Hopefully, I mean, if you are interested in learning more, and I can walk around and help you. You can also pull like Ubuntu machines, CentOS machines, Fedora, all the nice Linux distros are there. And once you pull something, it will look something like this. It's the name, the version, and a SHA-1, and then the size. And this size is virtual because it's Docker is doing efficient storage. If you, for example, run the Ubuntu machine, it will default to run whatever you point here. In this case, we're just printing hello world, and the container is stopped after that. If you do Docker run and then -- remove, whenever the container is stopped, it will actually remove the associated data. Every time you launch a container, it creates an environment, a file system. So whatever you write to that, it will be in that container until you delete it, or you can actually you can launch a container and then do something inside that container, and then if you stop that container and you commit that container, that will create an image of that container. And this is really useful because then you can kind of snapshot whatever you're doing. A lot of times we're working and we don't even know what we did, but it basically everything works now. So you want to snapshot that so that you keep it on the record. And the nice thing of containers is that you can snapshot that while you commit your container, and it creates an image out of it, and you can launch containers out of that image. And not only that, you can actually see the differences. You can say, show me what I did here with respect to the base image, and it will tell you, well, you installed this, or you executed these commands, or you saved this file, you changed this configuration file. It's like an introspection tool that allows you to understand what people did when you have to it's the same version for people that is familiar with versioning. It's the same semantics, versioning semantics taken to the world of machines, virtual machines. You can also create scripts that will be run and create an image. And actually, Unidata has a repository of images on the web. If you Google for Docker registry and then Unidata, you will see images for Jupyter, I think, or for IDB. Yeah. So you can actually compare if you installed IDB earlier and you installed Docker already, you can see what the difference is going to be, because then you would just say pull Unidata/IDB and you're done. That's the beauty. I think I'm okay. Yeah. Thanks. So we'll be around. Let me know if there's any question. I'm happy to help. Thank you.